Hello, everyone, and welcome to the Geek Nighter podcast. Today, I am joined by David Jacot from uh, Confluent. He's a Apache Kafka committer and a PMC member. And today, we are going to talk about Kafka Internals. Apache Kafka is a very popular streaming platform. People use it for different use cases to communicate between microservices, to do real time analytics for streaming use cases, and so many other use cases. And I've done multiple episodes related to Kafka and related to technologies around that. So if you are interested to check it out. But today we are focusing on the internals of Kafka and what happens when you write to Kafka or when your consumers are reading from Kafka, and how Kafka ensures durability and fault tolerance internally. And we are going to focus mainly on some of the general techniques that Kafka uses, and David is going to help us today to understand all of that. So I'm really excited, David, to have you here. Thanks a lot for joining. I know it's been months we were planning to do this, but finally it's happening. So I'm really happy. And yeah, let's start with a little bit of introduction for our viewers on what you have been doing at Confluent and with Apache Kafka in general.
Yeah, hi, and thanks for having me. I'm really pleased to be here to chat with you. Yeah, I'm David, as you said. I'm a really long time Kafka user. I basically started my journey like back then where Kafka version like oh 07 was released by Jay, June, and Neha back then. And I've been using Kafka since then. First, I started mainly as a user of Kafka where I use it in different contexts, startup, big enterprise, and everything. And 4 years ago, I basically joined Confluent to basically start working more like on the internals of Kafka. And since then, I became like an Apache Kafka committer and PSC member, as we said. And yeah, at Confluent, I've been focused on Kafka internals. I've basically touched like more or less like all the part of the systems. And nowadays, our particular focuses on the replication protocol and everything around how we do like group coordination to basically distribute partitions to consumers.
Yeah, that sounds really interesting. And I've also been using Kafka since a long time now, but very recently I've tried to understand like how things are working internally. So I think it's going to be a great learning experience for me as well. So for the viewers, most of you might have used Kafka for different use cases as I described initially, and but probably never really thought how things are happening internally, because Kafka provides you really nice abstractions, so you don't have to think about all the things internally. But there are some times that you really want to tune Kafka to make it work for your use cases. Of course, you can take some help from people from Confluent and people who work really closely with Kafka, but I really recommend understanding internals of such a amazing system that will definitely help you work with Kafka even better. David, I want to start with really basic here. In your view, so Kafka was created at LinkedIn, and since then it has evolved as an amazing technology, and it's not just one technology, but it's like an ecosystem that comprises of different technologies that work together to make such an amazing product. So, what is, in your view, Kafka today? How would you describe Kafka?
Yeah, if you look at Kafka from a project perspective, it's basically like a platform, I think today, which basically include like different pieces. The first one at the core is basically the Kafka cluster, which basically is like a pub sub messaging system where you can basically, publish events and then you can consume them with various APIs, right? And this is where you basically persist like all your events, you replicate them, you make them durable and everything, right? And then around that, provide various APIs. So you have like low-level APIs, such as like the producer or the consumer APIs, which basically allows you to interact with the Kafka cluster to publish and consume, right? But we also have a connect API, which basically allows you to either build your own connectors or use like connectors out of the shelves to basically integrate third-party systems to interact with Kafka. So for instance, if you want to move data out of Kafka to like a database such as MySQL, or if you want to take your Salesforce data and ingest them to Kafka. And we also have Kafka Streams, which is more like a streaming library, but I think you have discussed this like at length with Matthias in this show. So we don't need to discuss it that much.
You mentioned a couple of things there, like the producer and consumer API, and there's high level abstractions when you deal with Kafka streams. And yes, I've talked about Kafka streams in depth and exactly once with Matthias. So do check it out if you're interested. But today we want to focus mainly on like the core of Kafka, right? And let's say as a developer, I've been using Kafka. I know how these APIs work, but I've never really thought about the high level architecture or how these things are working internally. So when I look at Kafka at a high as a high level architecture, what are the
Mhm.
components involved there? So I know there is broker, there is partitions at a high level, but if we have to create like a block diagram, what are the components, major components?
Yeah. So the first thing I want to say is we basically support like two main architectures today because we are basically in the middle of this transition to move away from Zookeeper to what we call Craft, right?
Yeah.
So maybe I can briefly describe both architectures.
Yeah.
So if you look at the past, like a typical Kafka deployment consists of two main pieces. First, you have Zookeeper, which is basically used as a consensus slash metadata store for the cluster. This is basically where we store like all the metadata about the partitions, the
Mhm.
users, the topics and everything, right? And then you have the pool of brokers. And this is basically where we store like the data itself. So this is where we have the data persisted and everything, right? And this is where also we expose APIs for the produce API, the consumer API and everything.
Mhm.
In ZK mode, then like one of these brokers is elected as a controller, which is basically like the brain of the cluster, so to speak. This is the one deciding where the partition should be when there is a failure of the broker to basically reassign leadership and stuff, right? And this is like in a nutshell how like it works in the ZK mode. But this architecture has a few drawbacks because mainly we have to replicate like all the metadata in memory from Zookeeper. And just loading everything from Zookeeper into end memory takes a lot of time.
Mhm.
And this is why we thought about moving away from Zookeeper already a couple of years ago. And we started this craft journey, right? So in craft, Keeper is no longer there. Instead, we have built like a new controller, which basically rely on a slightly modified version of the Raft consensus algorithm to
Mhm.
replicate data. So in this world, we basically have a quorum of 3 or 5 nodes, which to do that the controller fits, and then the brokers are still doing the same, storing and persisting the data.
Okay.
This is like the two main high-level architecture that we support as of today.
Yeah. That makes sense. And I remember I was working with like Kafka and at a very high scale. And then Zookeeper at some point was a bottleneck. And then we had to ask the infra guys to do something about it. And then they had to scale Zookeeper and look at what is the bottleneck. So yeah, without Zookeeper dependency, it might even be better. So you don't have the deployments would also be easier. And also the maintenance and the performance would also improve is what I expect. Great. Talking about the coordinator, right? So, as you said, you have a pool of brokers, and one of them is the coordinator. So, is it okay to say Kafka has a leader based architecture?
Yeah, actually, we have a controller, right? And then we have coordinators, but those have a different role in the cluster.
Okay.
The controller is really about like replicate placement, handling failover of brokers and everything. Whereas the coordinators, we have two types of them. The first one is what we call the group coordinator, which is basically involved in the consumption logic to basically expose like the consumer group protocol, which allows like consumers to distribute partitions among the consumer group. And we also have a transaction coordinator, which is running. But yeah, coming back to your point about being a leader-based system, that's right. If you look at Kafka, we basically create like topic and partitions, right? And partitions basically are distributed in the cluster, and every broker is basically responsible of a subset of them. And for every partition, depending on the replication factor, that you have a leader and then you have a bunch of followers, basically replicating the leader to make the data more durable.
Yeah, okay, that makes sense. Since you talked about a few of the terms like consumer group protocol, and we talked about topics and partitions. In my understanding, topics are just a collection of items with that have the same meaning in your context that are grouped together and then managed together in your business context. And then partitions is something that is totally for making it horizontally scalable and such that is not backed up by a single machine and it can be distributed across several machines. Is that right to say? Or if do you want to add more to that definition? What do we mean by a topic and what do we mean by partitions?
Yeah, I mean, what you said is correct. So basically, like a topic is basically like a set of partitions, right?
Mm-hmm.
So the topic is basically just a name and a bunch of metadata. And then the data is really stored in two partitions, which are distributed in the cluster.
Yeah.
And the reason, as you said, is basically to basically allow us to scale out, right? If you want to
Mm-hmm.
produce more, you have to add more partitions to handle
Yeah.
the throughput, right? That's correct.
Okay. Okay. Perfect. Okay. So I'm looking at a pool of brokers, and there are producers who want to write data to the brokers, and data is stored on the brokers in persistent manner. And then there are consumers who are consuming from these brokers. So if I look at three boxes in a diagram, there is one box for producers, one is the broker, and it has a pool of machines. And then there are consumers, and then there can be hundreds of consumers as well. And then producers are basically writing to different topics, and they are
Mhm.
trying to collect their data or group their data in whatever business context it is. For example, if we talk about e-commerce, there can be an order topic or a consumer topic or a shopping cart topic or whatever, depending on what kind of data it is you're producing. And then consumers can consume data from these topics depending on what is their use case, and then do some processing and do whatever they want with the data. So let's focus on the first part for now, right? So the
Mhm.
producer is writing to a broker, and it has some data and it has some metadata, and the data has schema, right? So how is all that coming into picture? So as a developer, probably I define my schema, I write using the producer API. But what is happening when I call that write operation? Like, how is the broker interacting with the producer? How is it writing data to the disk? How is it making sure that it is durable? And how is it acknowledging back to the producer?
Mhm. Yeah, we could go through the right path, like piece by piece.
Yeah.
Let's start from the producer API, right? So let's say you insert like a producer in your Java application. We have this method to basically produce like a record to a given topic. So let's say you use that. You get your record with a key and value. You append it with the producer, right? The producer, the first thing it will do is basically check if the record has a key. If it has a key, we basically have to select which partition we want to produce this record to based on the key, right? And there, by default, it's a simple algorithm, just a key hash. The hash of the key mod, the number of partitions you have in your topic, and then designates like the partition you want to write to. But this part is pluggable, so you can also implement your own logic, right?
Mm-hmm.
So when this is done, the producer put that message basically in the buffer internally, right? And that buffer will basically be flushed out and written to the network layer, either immediately or at different interval based on the configuration of the producer, but we can maybe discuss this a bit later. And then at some point, it will basically issue what we call a produce request to the leader of that partition, then send the records which has been accumulated locally.
Mm-hmm.
When the leader receives the produce request, it does some validations to ensure that the record is valid. It checks the checksums and everything. And then it basically appends the messages to its local log directly.
Yeah.
When this is done, it basically put the request in a purgatory and basically wait until like all the followers have basically replicated the data to make sure that it's fully committed and durably stored. And when this is done, it will basically send back like the produce response to the producer, and the producer will keep going, basically prepare the next fetch produce request and send it, and it goes in a cycle like this, right?
Okay. Yeah. This is a fairly simple looking flow, right? But there's a ton of internal things happening. So first thing that you mentioned is producer is basically, I don't know if batching is the right word, but it is collecting
It is.
it is okay. So it is
Mhm.
basically creating a batch of requests or batch of data that it wants to produce to the broker.
Mhm.
And this is done mainly for efficiency, right? It cannot make a call to the producer, to the broker for each and every piece of data. So it's best to batch it and send one produce request to reduce the number of calls that it makes to the broker, is what I imagine, but correct me if I'm wrong. And
No, that's correct. We basically want to pack as many data as possible on a single request, right?
okay,
To
yeah.
basically fully utilize like the bandwidth, right?
Absolutely. Yeah. So
Mhm.
to fully utilize the network bandwidth, I want to make uh, batches of data and then produce that to the broker. Once broker gets it, you said it appends to a log. And so this log, when we say it appends to a log, it's already on disk, or is it just an in memory, like a log of data, or what is happening
Mm.
there?
Yeah, it's a very good question. So it's basically like a log on the disk, right? So like
Hmm.
every partition is basically really backed by like a physical log on the disk,
Yeah.
which is like an append-only data structure where we can basically write directly to it. So we don't cache anything on the broker, right? So one of the early decisions in the design of Kafka in the early days was to heavily rely on the page cache instead of
Yeah.
doing caching internally.
Hmm.
So from a broker perspective, we really write as fast as possible to the page cache. And then we basically delegate to the kernel to basically flush to the disk asynchronously, right?
Okay.
And the idea behind that is to basically have less writes and bigger sequential writes, so to speak, right? Because the kernel will basically accumulate everything in the page cache and then flush a bigger chunk to disk like regularly.
Yeah. Okay. So it basically reduce the copies of data that it wants to create and directly writes to the page cache, and then kernel takes care of flushing it to the disk, making it more optimized for the writes and not reaching the disk, like the actual disk, for every piece of data that it is writing, right?
That's correct. Yeah, that's correct. Yeah.
Okay. Okay.
It's basically more efficient. That basically like a more efficient way to write to the disk. And what's really interesting with that is it makes the internal of Kafka extremely simple, right? Because we heavily rely on the kernel implementation for this caching layer, right?
Yeah, that does make sense. And whenever people talk about Kafka internals, there's a concept called zero copy that people often talk about. So, is it something relevant here that Kafka has implemented? What is basically zero copy mean?
Yeah, it's a very good question. So we don't really use zero copy on the write path, right? Because
Hmm.
like we get the records in memory and then we put them into the page cache by using like a syscall, right? But we do use zero copy more on the consuming path, right?
Hmm.
So what zero copy is basically, usually when you read from disk, you basically, if you do it like a normal way, you basically get your data in the user space, right? So you move from the kernel to the user space and then you can do something with it. So if you will do that in Kafka, it means that you get your data in the user space and then you send them back to the kernel, to the network, right? To send back the
Yeah.
response, which is really not efficient. So instead, the kernel provide this zero copy mechanism via the send file syscall, which basically allows you to directly move bytes from the disk to the network without going through the user space.
Okay. Yeah.
So
So,
we heavily use that when we service fetch requests for the
mhm.
consumers.
Okay. Yeah. Probably we should go a little bit deeper on that when we focus on the read path as well. So moving forward on the write path. So what I've done is the producer has batched the request. It creates a produce request to the broker. The broker writes it to the local log, which is on disk, and then it makes this replication request to all the followers, is the
Mhm.
right term in Kafka world. And
Yeah,
then each of the follower also persists on disk depending on the replication factor, and then it get back that okay, it's done. And then once the configured replication is done, it gives that response back to the producer that it's done, and then producer can start working on the next batch of request. Is that the good flow?
that's correct. Yeah. Maybe I can add a few more details here, actually.
Yeah.
So the way the replication works in Kafka is that we have this notion of in-sync replica set, which basically represents like the replicas or the followers are basically considered a caught up with the leader, right?
Yeah.
So to be caught up, they basically have to keep fetching and remain within like a certain boundary, right? And if
Hmm.
they are not, they're basically kicked out of the ISR and considered out of sync by the cluster, right? So when you write Kafka, you can also specify like what we call the ACK settings. And there we support like basically three configurations. The first one is basically you can say, hey, I don't care about the ACK at all. I just want to produce. Even if it doesn't work, don't worry, I don't care. So in this case, we just write and then reply without anything. You can also say, I just want to write to the leader, right? So in this case, we ensure that the write to the leader is successful and then we reply. And then there is the settings called ACK equals to all, which basically mean that you want the reply of the produce request to be only returned when all the members in the in-sync replica set have basically acknowledges acknowledge that the records are fully persistent. Like the way replication works in Kafka is also a bit particular. So the replication is basically pull-based, which basically means like every follower basically constantly pull from the leader to replicate record. So they basically issue like fetch requests, which are the same used by the consumer, by the way. And then we constantly like replicate data, write to the disk, and then acknowledge whatever they have written, like in a SQL or in a loop like this.
Interesting. Okay, this is interesting, and I didn't really know. I knew that this is what is happening, but maybe I just forgot. So when you write the data to the leader isn't like pushing the data to the followers, but instead of that,
It's not.
the followers use similar to consumer group protocol, and then they create the fetch request from the leader and try to be as close as possible to the leader in terms of the data that is written to the log. And this is all configured on the producer API. So if a producer wants to be as fast as possible, but as that gives or that trades off the durability, so it can just write to the leader and get back the acknowledgement without waiting for the in sync replicas. Or if durability is a concern, then we can also wait until all the in sync replicas are up to the speed with the leader and then get the acknowledgement back, right?
That's correct. Yeah, that's correct. And there is like another setting I would like to mention here about durability, which is important. We also have a configuration on the broker, or can be per topic as well, which is called min in sync replica. Right. So as I said before, when you use like Axol, we basically wait until like all the members of the ISAR have committed, right? But there is a small caveat here, is the ISAR can go down to 1, right? If basically all the followers are, let's say, partition away from the leader, for instance, right? Which basically means that the ISAR is down to 1. So if you only wait on this, durability is not fully guaranteed, right? Because if you have ISAR down to 1, it means only the leader, right? This is why we introduced like this min sync replica to basically say, I want my produce request to be fulfilled only if I have that many replica in my in sync replica set, right? So usually we configure it to 2 to basically ensure that you have at least 2 replicas to commit your data.
And this is where knowing the internals make a lot more sense, right? Because just relying on the configuration acts all, assuming that you're getting the durability, but then acts all could mean that only one replica and that the durability is going down. But then when you also have a tuning ability where you say acts all, but the minimum in sync replica should be, let's say, 2, so that you have at least 3 copies of data, including the leader, that will increase the durability. So understanding the combination, how these configuration work. And Kafka typically, what I've seen is they provide a lot of configurability to the user.
Yeah.
I guess many of the developers that work with Kafka just work with the default set of properties that you get with the default deployable. And sometimes it's really critical, especially in production, that you configure or tune these configurations based on your guarantees that you want to provide. So this is really interesting.
That's right. And then I think if you want to be safe, you have to use like a replicated factor of 3, like a min in sync replica of 2, and then use Axol, right? I think this should be the default, right? And if you diverge from this, you have to understand why.
Exactly. That does make sense. So ultimately what you want to do is, in most of the cases, I would say in majority of the cases, you want durability of your data because you're producing that data. Unless it's like a click stream and you just want like a rough analytics on top of it, it's okay to lose a few events, but then only a few events, right? Even then, it's not okay to lose like entire batch of events and getting the analytics wrong. So I would say in majority of the cases, durability is really important and you don't want to lose your data.
That's right.
Yeah. Okay. So these 3 properties, and this should be the default to understand how your data exists on the brokers and is it really durable. So this is really cool. And just to dive a little bit deeper on the fetch requests that the in-sync or the followers are making to the leader, is it using the same consumer group protocol or it's just similar but different?
So there is no consumer group protocol at this stage, right? It's only like the fetch request, which is basically shared by the consumer and the followers.
Okay.
That's right. But the way it works is Like on every follower, you basically have a pool of fetcher threads,
Mm-hmm.
and you can configure the numbers, by the way, here. And then when a broker is told that he is a follower for partition X, it will basically go to that thread and say, hey, we have to fetch from this header for that partition. So go and do that, right?
Yeah.
So the fetcher will basically build fetch requests continuously and send them to the leader, fetch data, write to the disk, and then send the next fetch request to basically acknowledge that the data has been written, and then fetch the next batch and keep looping like this.
Yeah. And this is all asynchronous, right? Because the producer is just looking at if all the in sync replicas are up to the speed. But in a way, it's synchronous because the producer is still waiting for the acknowledgement depending on the configuration. But the broker or the leader itself is not replicating the data. It is letting the followers do that. And then does it check periodically that if all the followers are up to the speed before acknowledging, or how does that part work?
Yeah, that's a very good question. So to basically track what has been committed on the leader side, we have a notion of what we call the high watermark, which is
Mm,
basically like the offset of the record, which has been, you know, replicated and committed by all the member of the ISR, right?
yeah.
But when we have like a pending produce request in a structure which is called a purgatory, we will basically check regularly or notify this data structure that the high watermark has been updated. And when it is, like the pending request will basically check, hey, do I satisfy my produce requirement? And when it does, we basically return the produce request.
Okay. Okay. Yeah. So the concept of watermark here, like is it the offset, like highest watermark, or what does watermark mean here? So what is exactly stored in this data structure to identify, okay, where are my followers?
So the watermark is really simple. It's basically like a single number, which is basically like
Mm,
an offset. It's something we haven't discussed at length, but like basically
mm,
every log on the disk is basically an append only the structure where every batch written has like a unique offset attached to it, right? So we
yeah.
basically track the offset. We basically track the last offset. How to say that? I think the high watermark definition would be like the minimum end offset of all the followers, right?
Mm,
So we look at all the followers. We keep the one which is with the smallest offset, meaning that it hasn't like caught up to the leader yet. And
yeah.
we use that as a minimum to say, hey, this is where we are from the replication perspective.
So let's say, just to take an example, so I'm the leader. I have consumed, let's say, 160 records. That's my highest offset, assuming it starts with 1, 2, 3, 4 in an incremental manner. It might be
Hmm.
different, but that is all in implementation detail. Now, so I have consumed or written 160 records to my log, and I have three followers. One of them is at 152, the other is 160. Let's say it's already caught up. The other one is 155. So I'll take the minimum, which is 152, and say this is the
Exactly.
watermark, right? And one of the replicas still needs to catch up. And then when the high watermark, which is the minimum of all the followers, reaches 160, I know that all the followers have done that. So basically, high watermark is just one number that I'm storing, which is again makes it efficient. So, like storing all the information about where are my followers, it's just one number basically, right?
That's correct. Yeah, that's correct.
Okay, perfect. And then where is it exactly stored? You said it's in memory, or is it again like a log? Because it's again like a time series, right? It's happening every now and then.
That's correct. So the high water mark, we don't even persist it
Hmm.
because we can always recover it from the log themselves. So it's something we keep only in memory actually.
Okay. That's even better. We already have the log events, and then you keep a number in memory. And for each request, if it's already matches the requirement of min in sync replica or not, and then depending on, you just acknowledge back to the producer. Okay, perfect.
That's
Okay, so
correct. Yeah.
producer has written a batch, leader has made it durable locally, just writing to the local log, ensure the min in sync replica property matches, and give some
Mhm.
time to all the followers to catch up with the leader, and then sends the acknowledgement back to the producer. And this is all happening. So basically, for one produce request, there is a lot of things happening asynchronously on the broker, on the leader broker, and then the acknowledgement is sent back to the producer. let's talk a little bit about the failure modes here, right? First of all, before we go to the failure modes, I want to talk about the ordering part, right? So let's say I give 100 records in a batch of produce, right? How are these ordered? So if I talk about Kafka guarantees a single partition ordering, and if a record goes in a partition and then I write another record, those will be guaranteed in the same partition, those will be guaranteed in order. Is that correct?
That's correct. Yeah. Yeah. Once you
Okay.
write to the log, the order is guaranteed, right? That's correct.
Okay. And then this is happening because there's one leader which is writing to the local log. And if it goes to the same partition, the log entry that you're writing later or is in the next produce request will automatically go or will be appended. Okay.
That's
So
correct.
that makes sense. So what happens when things fail? Let's say the leader fails. Let's start from there. So I sent a produce request. The leader writes it to the log, the local log, but it fails. What is happening then?
Yeah. So what will happen if the leader basically has like a hard failure? And let's focus on the craft mode here. Basically, it's pretty similar. Like in the background, in craft, the broker heartbeats to the controller regularly, right?
Yeah.
So when you stop heartbeating now for a certain amount of time, the controller will say, hey, this broker is dead. So I have to move away leadership from that broker. So the controller will basically look at the member of the ISR and basically pick a new leader and elect it as a leader. And then it basically propagate the information in the cluster. So basically like a new leader is elected and the new follower are basically instructed to replicate from the new leader, right? What it means is if you have like uncommitted data on your leader, the one which just failed, those data are basically gone, right? They were not replicated. Right?
Yeah, exactly. So the local, so whatever leader went down, if the data was already only on that machine, it's basically gone, right? Or
Yeah, it's done. Yeah.
okay, how
Gone in the
does
sense, if the leaders come back afterwards, you may still have data on disk, right? But as the data was not replicated, right? When the new leader picks up, it was not aware of that, right? Which basically means that when the old leaders join back, it will have to erase those uncommitted records from its local log.
okay, 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 that makes sense. And so is the produce request failing here, or it's still waiting until the leader is
Now, as we discussed before, like the produce request is basically sitting on the leader and waiting there. So if the leader really fails, this is gone and the
okay,
connection will be cut. So it
okay,
basically means if we look at this from a producer perspective, the producer will likely get like either like a request timeout or maybe like a connection cut or whatever, and we'll have to retry like the batch.
okay. Yeah,
Yeah,
that makes sense. So it's per produce request that things are going wrong, because once a produce request is acknowledged, it means that all the min in sync replicas are up to the speed and the data is not lost because replication was over. And some
exactly.
of the out of sync replicas might still be trying to catching up. But one of those min in sync replicas that had already caught up with the leader would become the new leader depending on the leader election algorithm, and then the entire process will resume to its normal working. But the current produce request would fail. That's what is
Exactly. Yeah.
happening. And then the producer can always retry because it is not sure the data was written and replicated. And but is there a chance that it creates duplicates? Is it like a source of duplicate data, assuming the data was actually written and also replicated to one of the replicas, not all, let's say? So what is happening there?
That's correct, right? Because depending on at which moment like the failures happen, right? You can imagine a case where, like the records are basically written to the local log, basically replicated to the followers, and then you have the failure, right? Which basically means that we haven't had the time to acknowledge back to the producer, right?
Mhm.
So in this case, the producer will have to retry, but he doesn't know that basically the first request was actually successful, but not acknowledged, right?
Yeah. Mm.
And this is where item potency and transactions come into play if you want to protect yourselves against that. Yeah.
Interesting. Yeah. That makes sense. So basically, even if things go wrong, there are mechanisms that the cluster would auto heal itself, will create new, resume the process entirely. There might be some transient failures. The produce request might fail. You can always retry. There is nothing wrong. And then using idempotency and transactions, even if you have produced like duplicate data, you can deal with it in a different way. And most of the times, this duplicate data in a Kafka topic, for example, is not a big issue, but sometimes it can be an issue, and there are different ways to handle that. So it actually makes the architecture simple. So let the consumer of the data deal with the duplicate in events and data, and how does idempotency work, rather than broker itself trying to do things which are not 100% guaranteed anyways, because failure can happen, things can be written twice because there are retries happening. So I think that makes sense. Anything you want to add more on the right path that we might not have covered?
Yeah, there is maybe just one thing we haven't discussed at all there. We really discussed on the produce request class, right? Uh, but before that happened, there is something else that the producer has to do actually. It has to know where to send that produce request to, right? So for this, we have a concept of metadata propagation in a cluster. So basically, every broker knows everything about the cluster, where the partitions are, and provide like an API for clients to get that information. So when you produce, like the producer will basically request a broker in the cluster to say, hey, I want to produce to partition X, where it is, right?
Yeah. Okay. Yeah. That mapping, like where is the leader and where do I produce this request? And it might change, right? So by the time you're making a request, the leader might die, or it might change. And so it has to keep
Yeah.
getting that information for every batch. Is that correct? Or it just gets it periodically and assumes it is correct?
Yeah, it basically keeps it and refreshes it like periodically. And also like
Hmm.
when there is like a failure, such as a timeout or like a connection cut, it will basically assume that something got wrong and that's to refresh the
Yeah.
data to rediscover the
Interesting.
latest information. Yeah, but that's an interesting piece of Kafka because this cache is really like eventually consistent. So you may also have cases where, when the failure happened quickly, your producer may ask the broker, he might not be aware of where the new leader is directly. So there may be a
Hmm.
bit of back and forth there to rediscover where you have to go.
Interesting. Yeah. Cool. So I think at a high level and also at like internal level, we've talked about how the writes are working. So I have written my data in a durable manner. My data is in Kafka now, and I'm writing batches of data. The producer is doing his job. And basically this is the part where this architecture makes the producer and consumers decoupled, because we haven't really talked about the consumption part yet, but the data is still there and the producer isn't blocked. So producers and the consumers are decoupled, and producer does not know how many consumers I have. Now, coming on the other part of the block diagram that we initially created, there are different consumers consuming data from these topics. And basically, these are partitions and topics. To make it clear, topics are just like logical, right? And physically, there's only partitions inside Kafka, right?
That's right. Yeah, that's correct. Yeah.
Okay. So the way the topics are exposed, it's mainly for logical grouping of data, but internally Kafka only knows about partitions. So as a consumer, so before we dive deep into how consumers are reading data, what is happening there, at a general level, like the PubSub model, so the broker has the data now, and there are two ways the consumers can be made aware of this data. Either consumers can poll for updates periodically, or the broker can do the heavy lifting and push the data updates to all the consumer it has. So the basically we want to compare the push versus pull model. And here in Kafka, a pull model is used where consumers keep polling for new data. And so to compare pull versus push, is it because it simplifies the architecture that Kafka has decided to go with the pull model? Or how would it work if it was a push model at a high level?
Yeah, that's a very good question. And I haven't really thought about this recently. In my mind, I think the biggest benefit of the pull mechanism is basically that you basically move away all the tracking of where the consumers are to the consumer side. We basically mean that on the broker side, it's extremely simple, right? It doesn't
Hmm.
actually know, the leader doesn't actually know what has been consumed by the consumer or what's not, right? If we will have to implement like a push model, basically mean that we will have to track all this information on the leader and basically make sure that if a consumer fails and come back, we have to restart at the one right point and everything. So that would bring a lot of complexity to the protocol itself. I think in my mind, this is probably like the biggest reason why we move to this. We basically use this model, which is we basically allow to store like the data once, all right, and then the consumer at basically just pointers consuming from the cloud.
Yeah, that makes sense. And so, yeah, looks like simplicity is one of the major reasons why a pull-based mechanism is used instead of the push-based in Kafka, and the heavy lifting is distributed to different consumers. So they keep track of how far the data has been fetched instead of broker or the leader doing all the heavy lifting of keeping track of different consumers. And if the number of consumers are really high, it can become a bottleneck. So it also
Exactly.
probably makes sense at a very high scale when there are still high number of consumers, a wide variety or wide number of topics and partitions to deal with on the broker. That makes sense. So the data is already on broker. Now the consumers want to consume data from these topics, right? So what is happening there? Is it similar to the fetch request? And let's define the consumer group protocol first before we dive deep into that.
Yeah, so they have several steps, right? When the consumer subscribe, that's to discover metadata about the cluster as well. This is like the first bits, which is common to the producer, right?
Mm-hmm.
Then the second step is this consumer group protocol, right? So as we said, the basic unit in a cluster is basically like a partition. So if you have 10 partitions in your topic and you have like 10 consumers who want to consume for a topic, you basically need a protocol or like an algorithm to basically assign those partitions uniquely to every member in the consumer group, right?
Yeah.
Basically ensure that a partition will be processed by only one member. And this is where this consumer group protocol comes into place, right?
Okay. That makes sense.
I don't know if you want to dive into this protocol itself, but we can if you want.
Yeah, I guess let's focus on the read path for now. Like what? So assuming I have a bunch of consumers. So let's say for a topic like orders, whenever an order is created, I publish some data on this topic, and I want consumers to consume. Now, if I understand correctly, let's say I have a consumer group for the notification system. So whenever an order is created, this item or this message from the orders topic will be consumed by a bunch of consumers that are responsible for notifying the customers. So, okay, your order is created. So sending email, for example. The other consumer group can be for, let's say, analytics. So whenever I create an order, I consume this order created event from the topic, and I, let's say, increment a bunch of aggregation metrics, that number of orders created by a customer or something like that. And then there can be like others, like tens of groups that might be doing different things on this one event, which is order created. So I think at a high level, consumer group is clear, like what is happening and the number of consumers within consumer groups. So let's dive deep into a single consumer group. Assuming I have 10 consumers for the notification system, and I want to read data, and I don't want to read the same data twice. So how is that working, and what kind of requests the consumers are making?
Yeah. So the first thing is this consumer group has to agree on the assignment, right? So they have to decide who will consume which partitions in the consumer group, right? But as I said before, if you have 10 consumers and 10 partitions, basically like every consumer should have one and consume for that, right? And this is where we have this consumer group protocol, which basically allow the group to agree on an assignment. So the way it works, this protocol, it basically has two phases. This is what we call like a rebalance. So first, like every member will send like a join request to a service, which is called like the group coordinator, which is like a service hosted on the brokers as well. When like all the members have sent this join group request to the group coordinator, the group coordinator will basically send back the response for all of them, and it will basically elect a leader for the group. The leader, in this case, will get all the information about all the subscription in the group. Maybe they want to all subscribe to the same topic. Maybe they want to subscribe to different topics. Doesn't really matter. But the leader will take all this information into consideration and decide on an assignment, right? When it's done with that, they all send like a sync group request to the group coordinator. And the leader, when he does that, provide the assignment. And at this point, the group coordinator will basically send back the sync group responses with all the assignments for all the members, right? And from this point on, like every consumer can start to consume from the partition that has been assigned to them.
Okay.
This is like what happened like in a rebalance, right? When this is done, they start consuming. And in parallel to that, they also heartbeat to the group coordinator to basically signal that they're still alive and doing what they are supposed to do.
Okay. So the first step is basically getting assigned. So let's say there are 10 consumers. Each consumer gets assigned a partition. And this happens within the consumer group protocol where,
Exactly.
the assignment happens. And once this entire process is done, they also provide heartbeats that, okay, I'm still alive and I want to be part of this assignment and I'm still consuming this partition. And then once this is done, they start consuming, right? So what
Exactly.
happens? What do we mean by they start consuming? What kind of requests they are making to the broker?
So there are two things here. The first thing, they have to decide from which offset they want to consume from,
Mm.
right?
Mm-hmm.
So if the consumer group is fresh, they will either start from the start of the log or the partition or the end, right? It's basically like a configuration settings you have on the consumer, right? If the group is not new, it will basically, every member will basically ask the group coordinator for committed offsets to basically know where they left, where they were previously, right? And we start from there. When they have found the offset they want to consume from, they basically send like a fetch request to the leader and say, hey, I want the record starting at offset 100, for instance. On the leader side, what happened, if the offset is there and if there are data, the leader will basically reply and say, hey, here are the data, right? If the offset is not there yet, because you might be at the end of the partition already, the fetch request goes into, again, like a purgatory, and we'll be waiting like for a certain amount of time until data comes. And if no data comes, the fetch request is still fulfilled and return back with an empty result.
Okay. That makes sense. So offset is a very interesting concept here. Like you need an offset. Like where do you want to start reading data? Because it's not like get me this key or something, but it's like this is the point where I want to start reading the data. So let's say I start with the offset 100, which is somewhere, let's say, on the broker. So it exists. Now, what happens? Is it like a batch of data that the broker sends me back as a response? Or what configuration does control this behavior? What is the batch size?
So yeah, when you consume, you can basically specify like the amount of data you want to get back. You can do it per partition, per request, right? So you can basically say, hey, my request, I want a maximum 10 megabytes. And if you have 10 partitions, you can say I want maximum 1 megabytes for every partition. So basically ensure that you read from all of them and not only from one.
Okay.
So you get batch of records for that amount of bytes back. Then the consumer will basically does this thing, right? It basically provides those records to the application space, so to speak, right? So the application can process everything. And then we'll issue another fetch request with the next offset. And the next offset is basically like the last offsets you have received in your records plus one to say, hey, I want to fetch from the next messages on now.
Yeah, that makes sense. So I get a batch, and this batch is, so it's interesting. So it depends on the amount of data, like the number of bytes you want to read versus the number of records. So I don't say that give me 10 records, but I say give me 2 MB maximum, something like that, right?
Exactly.
So
Yeah.
what is the decision point here? Like why did Kafka decide to go with the amount of data as compared to the number of events, for example?
Yeah, it's a good question. So I think we have to go back to the produce bias again, I think, to answer the questions, because like when we basically write record in Kafka, we basically wrap the record into what we call a batch, really. Like really on the producer side, we create a batch of record, and this batch, you cannot split it anymore, right? Because it might be compressed, everything, it's like a single unit. And this is what we write to the log, right? So to the log, we actually write batch of records, right? So from a consumer perspective, when you know that, it doesn't make sense to say, give me 2 messages, right? Because you can basically split that batch, right? You have to take it entirely.
Okay.
And also, if you go with more like megabytes based or kilobytes based approach, it also give you like a high throughput, right? Because you can basically consume as much as possible.
Yes.
And really try to saturate your network again, right?
Interesting. Yeah, that does make sense. Since it is batched, it is compressed for performance reasons. It doesn't really make sense for the broker to know, okay, this is the nth record or something. So it just writes data in terms of bytes, and then the consumer is actually able to deserialize the number of bytes it has read and make sense out of it, because it all the data, it has a schema, it has some metadata attached to it, and the consumer can deserialize the data and make sense from how many number of records it has read, for example.
Yeah, exactly. The consumer knows the batch format, right? And what the consumer will do is actually unwrap the batch and provide like individual records to the user or to the application. Completely transparent, actually.
Yeah. That does make sense. Coming back to just a little bit more on this size of the batch. So let's say I say 2 megabytes, right? How do I decide? So as a developer, it's really tricky for me to decide like a good amount of data I want to read. So let's say I have 10 consumers. I just say read 2 megabytes. How do I know 2 megabytes is the right balance, for example, so that it doesn't slow the consumption versus it also optimizes the amount of bandwidth I use?
Yeah, that's a good question. Based on my experience, I think I have never seen anyone actually changing the defaults there.
Yeah.
So
Okay.
it's probably, I don't remember then, I think it's probably 10 megabytes for the request and then 1 megabyte per partition. And I think it just works well. But you have the ability to change that based on your workload if you want to. But I don't know any cases where we had to change that. But who knows? So I think there is no rules here. It's more you have to benchmark the system with your workload and try to understand the settings which work best if you have issues with the default, right?
Yeah, probably. Yeah. And Kafka gives you that ability. So Kafka comes up with tons of configurations and tunings, and probably the
Yeah,
defaults
too
work for
many.
you most of the times. And yeah, sometimes it feels it's way too many. And that's when understanding these configurations, and not just one configuration, like how does this configuration works with the other configuration that I have, because that might be canceling each other, for example. So understanding these configuration is really critical, especially when you're managing a Kafka cluster, or you're dealing with really high performance use case or high scale use case where every millisecond or second is important for you. um, Great. So that does sound good. So as a consumer, I'm requesting give me data maximum, let's say 10 megabytes. I'm using the defaults, starting this offset, and the broker gives me the data. I process it. I do something. Let's say I do some counting, very basic stuff, and then I commit. So there should be a commit, right, or acknowledge, where I say, okay, I commit that I have processed these events. So give me the next batch. So how does that work?
Yeah. So there is just one thing about to add before we jump into this, just to close on the fetch request processing. There is something I did not mention is like when you request an offset on the broker, basically the broker ensures that it only delivers data which are committed, right? So coming back to the high watermark concept we mentioned before, right?
Yeah.
It will basically, basically the high watermark is basically like the latest point you can consume to. You cannot go
Yeah.
beyond that, right? Possible. That's
Mm.
important to understand because without this, you will basically consume like uncommitted records, right?
Yeah.
Yeah. Coming back to your question about how to commit the work you have done, as we discussed earlier when we described the pool-based model, we basically said that like the offset tracking is completely independent from the consumption path. It's basically the responsibility of the consumer to checkpoint what has been done. So for this in Kafka, like the group coordinator service we discussed before that provides like the consumer group membership / rebalance protocol also provide like an API to commit offsets, right?
Yeah.
So what will happen on the consumer is that whenever you process records, you can say, hey, I want to commit that offset and say, yep, and then send it to the group coordinator to persist it. And you keep going. You process records, then you commit your progress, you process the next record, you commit your progress, right? And there you have some maneuver in a sense that you can choose if you want to commit like every single messages you have consumed, right? Or if you want to be a bit more, let's say, laxist and say, hey, I want to basically commit only every 5 seconds, right? Because that might be enough for your use case.
Interesting. Yeah. Okay. So it again depends on the consumer that, okay, I have committed my work and I say, okay, give me the next batch. And then the this commit or what, so it again, I guess it's again like a number that is stored on the broker that for this partition, for this consumer group, for this consumer ID, this is the offset that is committed. And then that cannot be read again, right? So that is okay. This is done. And I always read like the next set of offsets.
Yeah, it's a bit more nuanced than that actually, because the way we commit offset is correct, right? You basically send like a request to the group coordinator and say, hey, I want to commit that offset for that consumer group and that partition, right? But then, right, it's again like the consumer that we have to basically retrieve that offset to start consuming from that, right? So for instance, if you have like a buggy consumer which does not do this properly, it will not work entirely, right? So when the consumer gets a partition assigned, the first thing it will do is it will go to the group coordinator and say, hey, I have committed something for those partitions. And if yes, please give me the offsets. And I will start from there, right?
Okay. Yeah. Yeah. That makes sense because consumers can also die. And when a consumer is died and the new consumer is taking up that partition, because rebalancing will happen and the assignment will happen again. So the new consumer that wants to read wants to know what all work was committed. And so deduplication of work is happening basically. And then it will start from the work that was never committed. Even if it was partially done, it's again duplication of work, but that's when the idempotency comes into picture. But whatever offsets were committed, they won't be read back to a different instance of a consumer.
That's correct. Yeah, that's correct.
Okay, perfect. And so the consumers are reading data, and let's talk a little bit about the configurations that is available. So as a consumer, I have to give an offset and the amount of data I want to read. And of course, there's a configuration. You can change that, but defaults work great. What are the other configurations? So that can impact the speed at which consumption is happening. So there's the batch size definitely, and then there could be like the amount of time it waits to consume the next batch and things like that. So what are the things that handle the performance or the speed on the consumption side?
Yeah, everything related to batching is more on the produce side, right? Because this is where you decide how many bytes or kilobytes you want to pack per batch and everything. The side, you cannot change that at all. Just rely on what has been written to the thing. The only thing you can configure is like the amount of bytes you want to retrieve per partition, as we discussed earlier.
Yeah.
So from a consumption perspective, there is this plus like the amount of time you are ready to wait if there are no data. I think this is 500 milliseconds by default. I don't know if there is like a really strong reason to change it, but depending on the workload, it might be something to look into. Yeah, I think the optimization point is more on the consumer group protocol probably, because depending on how you configure that, you basically have to choose which assignment algorithm you want to use to basically assign those partitions. And if you use like the default, which is what we call the range assigner, which is basically the way it works is if you subscribe to multiple topics, it will basically ensure that all the partitions are basically aligned, right? Basically the first partition will be assigned to one member. The second partition of all topics will be assigned to another member, and they will always be aligned and stay together. And this basically allows you to basically join stuff between topics, right? If you align partitions. But the caveat with this default is like, whenever there is like a failure or like a scale in or scale out event, like the consumption has to stop. So basically, we basically trigger like what we call a rebalance, which basically means that all the member has to stop consuming, they have to commit their offsets, and then they rebalance to reassign partitions, and then they can basically resume, right? During this rebalance time, which can take a few millis in the best case, maybe 1 minute in the worst case, if you have like bad members in your group, that will basically stop consumptions, right? Which is pretty annoying.
Mhm.
So this is why we have another protocol or like an extension to this protocol with a new assigner, which is called cooperative sticky assigner, if I remember correctly. And basically this one allows to, keep consuming and processing
Mm.
records while you do like the rebalance event. So yeah, it's something to be aware of. Consumer group, like a place where we have had actually many issues. And this is why we have decided like last year to completely rework this part. And we are basically working now on a new KIP now, like a Kafka improvement proposal, which basically proposes like a brand new protocol to do this partition assignment for customer groups.
Interesting. Yeah, that's good to know. As someone who wants to consume data from a topic, let's even start before that. So I want to create a topic, let's say orders, right? And while I'm creating a topic, actually what I'm creating is a set of partitions on Kafka, right? And I have to provide the number of partitions I want to create for a topic. So how do I get a good balance so I don't create like too many partitions and I don't end up creating very few partitions that might impact the performance? So how do I go about it? What is the general recommendation there?
That's a very good question. I know. And I would say this is more like an art than a science. So yeah, I think that the thing you have to be aware of is it really depends on your use case. So first you have to understand if you want to use keys for your messages, meaning that you want to really ensure that all the messages for the same key goes into the same partition. If you are in this use case, like the number of partitions you pick is extremely important because it basically means when you start with X, you're basically stuck, right? You cannot add partitions, you cannot remove partitions because that will completely screw up like basically the key assignment of your
Yeah.
records, right? So in this case, you have to really think about your workload, your like throughput, and I would probably advise to over partition a bit. Maybe have too many partitions, not enough, right? So if you go with 50, that might be better than 5 if you don't really know what's coming, right? However, if you don't use key-based records, you don't care because then you can add partitions and you can basically scale out without any issues, right?
Yeah, that makes sense. And the cases when I can imagine you want to use a key based partition is basically when you want the same or the records with the same key in one partition. So you can either do some processing on the consumption side, and it's easier to manage because one consumer has all the data for a single key. So you can, let's say, do some in memory counting or some processing or some aggregation. And I think it's very critical in some of the stream processing use cases where you key your data that it goes in the single partition, and then stream processor itself can do the processing. But for general use cases where you just want to pass data from one system to another, or you can connect microservices, things like that, probably keying of the data is not that important. And then having the random key generation or the hash based that comes default might be more suitable, so you can increase the number of partitions without any problems in the future.
Yeah. So one position is if you don't have a key for your message, it's really random, right? The producer
Yeah.
picks like one partitions in a topic that. I agree with what you said, right? I think it really depends on use case. Another property which is really important when you have this key-based producing is also about the ordering, right? Say that you have like all the events for customer in one partitions, you want to have them in order, right? So that when you consume them, they make sense. But otherwise, if you have reordering, you can basically screw up everything.
Yeah, that makes sense. And even to deal with that, like ordering again depends on the use case. There might be some property that you can do some reordering at the consumption level. For example, like sometimes ordering is important but not as critical. For example, you read some events that order has been created or shipment has been created, something like that. In the business context, you already know that if a shipment is created, order was already created. So even if they come out of order, you can simply discard the order created event or assume it already happened, and the ordering or the reordering can be done logically. But in some cases where
That's
the
true.
ordering really is critical, probably it makes sense to have a key based partition. So you get your data ordered in a single partition. Yeah, I agree.
That's correct. Yeah. Yeah. And yeah, I think this is really like a limitation of Kafka today. I really wish that we can maybe relax this constraint in the future, and maybe by having some way to dynamically change the number of partitions while preserving like the ordering.
Yeah.
That would be awesome if we can get to that at some point.
Mhm.
But this is complicated.
This is already complicated. Yeah.
Yeah.
Okay, cool. On the other side, when I create like the number of consumers in a consumer group, how does that impact something on the broker side? Because let's say I create, of course, I can create more number of consumers than if the topic has partitions, but then those consumers will be basically useless because they won't be assigned any partitions, right? Because if I have 100 partitions and I create 200 consumer threads, those 100 consumers will be sitting idle and doing nothing because they're not assigned any partition, right? So the maximum number of consumers I can have in a consumer group is the number of partitions, basically. But typically,
Yeah, that's correct.
yeah, but typically I have less consumers and more partitions because each consumer can deal with multiple partitions unless that creates a problem. So does that even create a problem when there are more number of consumer groups for a topic? Is there a like a maximum number that Kafka supports? Or I guess what I want to ask is, if there are like hundreds and thousands of consumer groups for a single topic and they are all reading the same piece of data, what is w- can it create a problem at the broker level?
So if you have a single consumer group with 1,000 members consuming from the same topic, I think from a consumption pass perspective, that's not an issue, because if you have 1,000 members in one group or 1,000 groups is one member for Kafka, it's basically the same. It's just a fetch request that it has to service based on offsets. And this is again one of the advantage of like the pool-based model that we have, right? It basically doesn't matter, right? However, I think the limitation is more like on the consumer group rebalance protocol, right? There we have seen that when you go in the thousands, it really gets like unstable. And this is one of the reasons why we are completely redesigning this protocol from zero.
Perfect. Yeah. So yeah, probably in future even that issue will be gone, and there's a lot of active development going on in the Kafka community, and that's what makes Kafka so special and is so widely used because people know that there's certain type of guarantee that okay, if there are issues they will be fixed. So great. I think we have covered a lot of details on the internals of especially the write and read path, the consumer group protocol, the limitations and the design decisions between pull and push models, some of the very critical configurations. Of course, we cannot discuss all the configurations and a lot of configurations because there's limited time, but these are all interesting discussions. The last thing I wanted to ask you is your opinion on Kafka being called as a database. Like traditional world database are the ones that provide the asset guarantees, and you can have your transactions and all that with asset guarantees, and the application is really simple because the transaction is gone and taken care at the database level. From that to the more modern world where there is a ton of key value databases with different structures of data and really horizontally scalable, where do you see Kafka if we talk about the spectrum of databases?
Yeah, it's a very good question. I think it really depends on the definition of what a database is. I think
Yeah.
the common definition when you say database, people expect tables and then SQL and stuff like that, right? So from that regard, like Kafka is not a database. However, if you look like inside like a database, like they all have something in common. That they have like what we call like a commit log, right? To basically process the data and then replicate the data between instances, right? And Kafka is a commit log as well, right? So the way I see it is more like Kafka could be like a piece of building like a database like system, because it provides like the core capabilities to basically have that commit log with transactions and everything, but it doesn't provide like the piece which basically materialize the data to be queried, right? So if you put Kafka plus that piece, could be Kafka streams, could be whatever system, then I think you can probably build like a database around Kafka, right?
That's cool. Yeah. And I think I agree to that. If we just take Kafka, it's not really guaranteeing you anything like a database, but Kafka enables you to create one for your own use case. And as you said, Kafka streams, it also gives you KSQL. You can write SQL queries to query your data and all that. So yeah, good to know your view on that. So I think unless you want to add something there, I think we have covered good depth in terms of how Kafka works internally and some of the key configurations that people need to keep in mind before they deal with Kafka in production. So thanks a lot for adding the coming to the show and adding valuable insights to the discussion. And I'm really looking forward to collaborate with you more on Kafka topics. And I really hope it provides a lot of value to people who are new to Kafka or have been working with Kafka but never went to understand internals. And they will be curious to know more. So they can definitely look at the official documentation presentations in from the Kafka Summit on Confluent website. So thanks a lot, David, and thanks for being on the show today.
Yeah, awesome. Thank you so much for having me. It was really a great conversation, and I really hope that content is helpful for your audience.
Absolutely. Thank you.